Your time for taking it. My time. Of course, we have stepped in the last lecture, but I will repeat it now. I would welcome questions during the lecture. Anybody who has any questions, please type. No question is a bad question in a class. Every question that you ask helps others to have a better perspective. And I'm sure you will ask when I am not very clear in telling you good things, or when you have not been able to draw any good conclusion from it. A couple of announcements. Number one is about a video source from MIT. MIT Open Source Resource has a very good set of lectures, video lectures, given by the chemistry professors. They are very good lectures. And they also accompany lecture material in PDF format. So you can download that and you can also go through those lectures. But certainly, when you look at that kind of resource material, it can only be supplemental. Supplemental in the sense that you cannot afford to just go and rely on that. That is a non-interactive system. You can't ask questions, you can only listen. And number two, you do not get any of these exercises and problems that will be a part of this whole course. So I'm sure you will like this set of courses, set of lectures, and that you will take it only as a supplemental thing, not something that you should take to be a substitute for this set of lectures. Number one. Number two, initial lectures that I have given in the last lecture and in the coming lectures are from the book Resnick, Halliday and Crane. And I did not see any set in the library. It is available in the market, you can buy it. It's a very good book. But what we have done, what Shama has done this morning, is to scan the relevant pages today and post it on the resource page of LMS, so that you have those pages available. And then a few more pages remain that she will do tomorrow. So you will have the relevant pages from that book available on LMS.
Repeat the name of the book.
Resnick, Halliday and Crane. It is this is in the course description also. If you look up the course description, you will see this book coming. The first book description. And it is only meant for the first few lectures. And then you will go to take help from other books also. I have a couple of notes from my last lecture. I would like to, I described Zero's law of thermodynamics. And I am revisiting it. And Zero's law of thermodynamics are described as law of equilibrium of states. Systems in equilibrium. How would you say two systems are in equilibrium with respect to each other? You measure that by their equality of their temperatures. So you say two systems are in thermal equilibrium with each other if they are at the same temperature. And hence the famous statement that if A is in equilibrium with B and A is in equilibrium with C, then B is also in equilibrium with C, amount to saying that all three have the same temperature. Okay? But then this leads to thing that I forgot last time was that this leads to the concept of heat reservoir. Heat reservoir is a thermal reservoir as against the description of thermodynamic reservoir. Thermal reservoir, heat reservoir is a system which is supposed to be very large and contains a large amount of energy and is at a T. Now the purpose of this heat reservoir is that if any system is brought into thermal contact with it, then the system brought into contact will acquire the same temperature. So you bring the test system into contact with it, then if the temperature of this test system, say T0, is different from the temperature T of this, then there will be a heat flow from one side to the other. If this temperature is larger than this temperature, then heat will flow from here to here. If this temperature is larger than this temperature, then heat will flow from here to here. So there will be an exchange of heat if temperatures are different. All right? And when there is the exchange of heat, the exchange of temperature, there is a rise of temperature because of exchange of heat. And this exchange of heat lowers temperature. Okay, suppose T naught is lower than T. Then exchange of heat would lower the heat content or the energy content of the reservoir and increase the energy content of this system, and therefore will increase the temperature over here and decrease the temperature over there. However, this system is supposed to be so large and the heat content of this system is so large that a small amount of donation of heat or energy to this system wouldn't really affect the temperature of this. So when the other system is brought into contact with this, there will be an exchange of heat, but this system is so large that its heat content remains unchanged, and therefore the temperature remains unchanged. And therefore this is a source of defining temperature. So heat reservoir is a source of defining temperature T. Okay, this is an important thing, and you will come to various different kinds of reservoirs. This is of course a concept, and this concept is a mental construction. But it is not very far from actual reality. So suppose we are at this ambient temperature of say 21 degrees over here. And if you open the windows over there, then there will be an exchange of heat between outside and inside. And then very soon we will feel the temperature of the outside region. There will be an equality of temperature of the outside region and the inside region. But that will actually not affect the temperature of the outside region, because the outside region is very large. It is a heat reservoir for us. So this happens all the time around us. System, and there is a heat reservoir. So we at times are the system, and the room is a heat reservoir. This room is a system, and the outside world is the heat reservoir. Similarly, there are other reservoirs. There is the particle reservoir, which lets particle be exchanged with a test system. So that over here we have a finite number of particles over here. And if you open the windows, particles will flow in from outside or from inside. They will flow this way or that way. They will exchange particles. But that will actually not quite affect the particles outside. What would cause particles to be exchanged? Force that, no, force, I'm using the wrong word, it's not a force, but the quantity that causes particles or matter to flow, to be exchanged between systems, is chemical potential. So like temperature, chemical potential is another quantity. If the chemical potential of the outside world is the same as that of the room over here, there would not be much exchange of particles between the two systems. Like if the temperature outside is the same as temperature inside, there would not be any flow of energy and heat between the two systems. So chemical potential determines, if there is a difference of chemical potential, then particles will flow. Suppose we have here the lower chemical potential, outside world is the higher chemical potential, we open the window and particles will flow in. So we have therefore various different kinds of reservoirs. I described these two important reservoirs which are essentially multi-constructions as far as we are concerned, but they actually are around us all the time. We use heat reservoir, a thermal reservoir, so that we can connect our system to that reservoir, and then the temperature of the reservoir will become the temperature of the system. So we want to fix the system temperature, and we do this with the help of. Okay.
So we use the heat reservoir to, you said, define temperature, or actually the
Right.
Right. So what do you do with the particle reservoir? What do you define?
Chemical potential, as I said. So if suppose you have a chemical potential mu naught of this system and a chemical potential mu of this system, and they are different, then particles will flow from this side to this side, or this side to this side, until they are equal. Chemical potentials are equal. So then this system would acquire the same chemical potential as this system, reservoir. And although exchange has taken place, but the chemical potential of the reservoir will not change because it is so large. Okay? So that answers the question. Okay?
So what is the chemical potential?
Okay, so let us take this to be the definition of chemical potential. Chemical potential is a potential, the difference of which will cause particles to flow. But this is something which is a very important concept in chemistry, because that determines chemical reactions in systems. Okay? So for the moment, let us find it to defining it as this quantity with the difference of which causes particles to flow. Any more questions? Okay. So then the other thing, the important thing that I wanted to emphasize, importantly, that heat is not something. Actually, I said that in the last lecture, the day before, and this was towards the end of my lecture. So somebody came and asked this question, and therefore I realized that I need to explain this in detail. Okay? Heat is not something that resides in the body, that becomes a property of the body. Heat is not to be regarded as property of the body. Energy, on the other hand, is a property of the body. Energy can be contained in a body. What is heat? Heat is only when energy flows. The flowing energy is called heat. Okay? So, heat is energy in flow. This computer, thank you very much. Now, reminds me that I have to switch off my mobile. Okay? So it reminds you also. All of you who have not yet switched off the mobile, please do that now. So this heat is energy in flow, and heat is only energy in transit. Similarly, work that we are so concerned with in the discipline of heat and thermodynamics is again something which it doesn't reside in a body. The body uses some energy from it to perform some work that you see. So it is again an energy that is used to perform some work. Okay? So this is again not something to be taken as. So these are Q and W. Heat is I write as Q and work as I write W. Are not, do not. Heat, Q and W do not describe state of a system. Okay? And when the system, okay, we will come to those things later. And what is important is that what describes a system, state of a system, is described by some variables. So I should have started by saying state variables, headline, state variables, and then wrote down those, and could have written down those things. I'm just saying that the state of the system is described by some variables. These are pressure, volume, temperature, number of particles. These are contained, these are the property of the system, the state of, property of the state of the system. These would describe the state of a system. Temperature would describe the state of a system. Pressure would describe the state of the system. Volume and number also describe the state of the system. And therefore there are actually a few more of such functions. And these few more such functions would actually be what we call functions of state. Functions of the state are such that if you were to take a hypothetical space in which the state is defined in some manner, and if you take a particular, suppose this is a space covered by these functions of the state, these variables, and you take only two of them, P and V. This is the normal practice. You already are familiar with this. Then any point in here describes a state of the system, because that has a particular value of B, has a particular value of P. Similarly, if I could draw a four-dimensional space, I would be able to specify a point that would have a value of P and V and T and N. Okay? Now, if you increase volume from here to here and decrease pressure from here to here, then increase volume from here to here, and then come back to this pressure, the point is that the value of the pressure will be the same as the final value of the pressure would be the same as the initial value of the pressure, because pressure is actually the property of that property of state. It is the property of that point, the value at that particular point. So that will not change. It will be the same when you come back to it. This is a definition of function of state. The function of the state has a value assigned to a point in that space. Why I don't have white chalks today? White chalks नहीं यार. Oh, चलो आज
Yellow.
So I hope you don't mind the red and green and blue and black chalks.
Yellow.
Black. Okay. So let me start defining a few things and then take you back to some of the physics that you learned in your A-levels class. I will also define what is called an ideal gas. Ideal gas is a gas, which is defined for the purpose of simplifying things, and the simplifications are in terms of no interparticle interactions. This is the peculiarity of an ideal gas, and to ensure that there are no interparticle interactions, what you do is you take it to low number density. When you take it to low number density, then actually you are saying that there are very few particles in a given volume. Therefore, the average distance between particles is large. And if the average distance between particles is larger than the range of their interaction between each other, then they are not interacting with each other. Okay. So, average, no, I'm not writing large enough. Low number density means average distance between particles is larger than range of interaction. And if we can ensure that, then we have an ideal gas. And therefore, because of this, we have large volume per particle. Large volume per particle means that if you have V is defined as V per N, V divided by N. V is the total volume of the gas, and N is the total number of particles of the gas. Then large volume per particle is large value of the small v. Okay? We will also define something as we go on, because that is an important thing. The value of mole. Mole is something that, again, mole number is something that you're familiar with. You have solved, problems because dealing with the mole number. But I thought before we go any further, let me take a minute to bring you back to it. This is quantity of substance. Okay? You can have molar mass, you can have molar number, you can have molar weight. 1 mole contains, this number is 6 times 10 to the power 23 particles. These particles could be atoms, molecules, very small molecules, very large molecules, whatever. You can have a diatomic molecule, you can have a triatomic molecule, you can have a DNA molecule, anything, small or large, unit. This particle is that unit, and there will have to be 6 times 10 to the power 23 of them to be called a mole. Okay? And a molar volume, therefore, is volume occupied by 1 mole. So I will write this with a small n at the bottom. Subscript, this is total volume divided by the number. Okay, this number is this number, sorry, is, you must have already Avogadro number, okay. This is the importance of Avogadro number. You know, you define mole as a quantity, as a unit of quantity of substance, which would mean that you don't actually have to worry about that particular quantity having 1 particle or 2 particles or 10 particles or a million particles. Your mole will still be a mole, a unit. Okay?
I want to ask a question about the ideal gas. There are no interaction between the particles, or there is a different distance between them because of which there is no interaction?
It means the same thing. The question that he asked is that when you say that there is no interparticle interaction, no interaction between particles, is it the definition of an ideal gas, or is it because there is an interaction between particles, but that particles are so thinly occupying the volume that there is no chance for them to interact? This is the question, okay? Which actually, as far as we are concerned, and defining an ideal gas means the same thing. Suppose you have a gas in which particles do not interact with each other at all. We would call it an ideal gas. However, it will be very difficult to find particles which do not interact with each other. They will always have some kind of interaction with each other. Masses interact with each other according to Newton, and you have electronic orbitals overlapping, and therefore you have van der Waals equation, forces, and so on and so forth. You have a lot kinds of interaction between particles. So you can't have actually a system without any interaction. What you can actually you can create such a situation by doing this, and that is why we call it an ideal gas. Yeah.
Would that be volume over number of moles?
This molar volume is no volume occupied by a mole is number divided by the Avogadro number will be the molar volume. Okay, is that any confusion over there?
It should be the number of moles.
Because we have that would be volume per particle.
So okay. This is okay. Now let me see what I'm trying to say over here. Maybe it's a question of interpreting this quantity. Let me see. If I say volume per particle, so I am given a particular volume, and I have n number of particles. Then volume per particle is what I call V equal to capital V over capital N. Okay? Now, when I say, if I were to say volume per mole, then yes, volume per mole will be V over number of moles. Okay? And number of moles is defined as small n, okay, small n. And you say volume per mole is equal to this quantity. What I had over here is that if you divide V by n, you get volume per particle, and if you divide it by Na, what you get is that you have Na number of moles in the substance, right? Na number of particles in a mole. Okay, so you are right. Actually, what I should do is I should not call it molar mass. I should call it something else. Okay, so good. I take your point. This should be what molar volume should be. Okay. Okay, good. I'm happy people are attentive. I would now go on to describe what is called gas laws. Gas laws. Now, gas laws are some empirical laws obtained from observations in laboratories, and they are supposed to be approximately true for nearly all the gases. And these are important because they give rise to relations between these state functions. We need to find a relationship between these state functions, and that relationship would define characteristic of the system. That relationship between them will be called equation of state. So gas laws will help us write down equation of state. The first one is that at constant pressure and temperature, V is proportional to n number of particles, which is obvious, which is very, very obvious. Okay? This is we could easily call it law of balloons. You put in more particles into the balloon, the balloon expands. So, and this you can write as V equal to some constant C1 times n, and graphically this will be a straight line that perhaps will go like this. The slope is a unit slope because it is proportional to n naught. Okay, and slope is equal to C1, the constant. And constant will be taken care of later on. The second thing is that at constant temperature and n, volume is inversely proportional to pressure, or pressure is inversely proportional to volume. I should write it as P times V equal to another constant C2. And when P and V are related to each other inversely, then this diagram, which we often draw, in fact I drew it over here too, this would be more like a hyperbolic function that goes from here to here, will basically go to 0 on this side at infinity, and will go to 0 for volume at infinite pressure, and so on. So this is how this looks. This is called Boyle's law. A third law is at constant P and N, volume is proportional to temperature. So that we will write V as C3 times temperature. And again, like that curve over here, we will have temperature on this side and volume on this side, and this will again be a straight line. Now we can combine them. In fact, we can draw some conclusions from it. From here, now let me make use of this freedom of using colored chalks to write my sort of between the line statements. From here I can write P1 V1 is equal to P2 V2 because that will be equal to constant. Same constant will apply to the values V1 and P1 as well to value P2 V2. So P1 V1 is equal to P2 V2 is a logical outcome of this statement. Similarly, V1 over T1 equal to V2 over T2 is the logical outcome of this statement. In fact, I can write down a fourth statement also. The fourth statement would be at constant P and I have written that at constant V and N, P is proportional to T also. From which I can also say that P1 over T1 is equal to P2 over T2. Okay? So we have therefore these deductions from these laws. And you can put them all together. You can put them all together in the, remember, V is equal to this constant times T and V is equal to this constant times N. So V is equal to some other constant C4 times N and T. And also V is proportional to 1 over P, so one can say V is equal to yet another constant times N times T over P, because V is inversely proportional to this. So we could in fact have this kind of relationship between them with a constant outside, and this constant will be what we call K. The K will be the Boltzmann constant. And the value of it is 1.38 times 10 to the power minus 23 joules per degree Kelvin. Okay? And one fact, one can write number of moles equal to N over NA. N over NA is number of moles. Okay? And therefore, one can write this relationship for N. One can write, and this number of moles is we write small n. We had done that earlier too, small n. So this relationship means that N, capital N is equal to small n times NA, and you have therefore this relationship written as V is equal to K times, and N is replaced by small n and Avogadro number NA times T over P, and K times NA is another constant, we call it R, and give it a name, gas constant, a universal constant again, and R, the value of R is equal to 8.3145, if you want to be very exact, joules per mole per degree Kelvin. Okay? You can check, verify, to see if this is okay. And R has this same value for all gases, this is a universal constant. So you therefore have similar to this expression over here, I could write down from these yellow expressions T1 V1 over T1 equal to P2 V2 over T2. This certainly would be very, very familiar to you because you used these relations a great deal when you study thermal physics in your intermediate or A-levels. Okay? These relations like this, and then of course this equation of state. What we have obtained at the end, these two relations, PV equal to N times K times T, or PV equal to N times R times T, are the ideal gas equations. Equation of state. Same equation of state that we were trying to think of over here, finding a relationship between these variables. So we have for ideal gases, and from gas laws we have found this relationship. One of these, Boyle's law, is used to define the absolute zero scale of temperature, and I thought this is something that you already know, but because there's one important point that I would not like to deviate from this discussion. The point is that the important point is to go from ideal gas to real gas. How would the equation of this equation change? PV equal to NKT or nRT. How will that change when we go to real gases? Okay, when we say P equal to, for ideal gas, P equal to NKT over V, it amounts to saying that volume can go to zero, and therefore at that point pressure will go to infinity. Well, we had a feature also. As volume goes to zero, pressure goes to infinity. Alright? But in real substances, particles will not be able to come closer than a particular distance with respect to each other. They would actually resist volume getting to zero. Volume cannot get to zero. So if volume cannot get to zero, volume can get to perhaps some minimum value. Okay? So if it can get to some minimum value, so interparticle repulsion repulsion, or in which they will not let other particles come very close to each other, would lead to something like NKT over V minus some B. Volume cannot be smaller than some minimum volume, and that minimum volume is called V. Okay? So that aspect will tell you that for real gases, this particular part should be. On the other hand, in real gases, there is interparticle attraction. When particles are too far apart, they don't know each other. There is no interaction. When they come close to each other, then there comes a time, there comes a distance when they would start to feel each other's presence, and that actually is the range in which they start to attract, to attract each other. And then, if they come in still closer to each other, then they will start to hit that strong force of repulsion, and they would repel each other. So repulsion we have taken care of. Attraction is something in which we should be able to express that there is this attraction. That attraction would be for pressure. Attraction would actually reduce the pressure, not increase the pressure. Okay, because this will bring particles together, and that is something which happens to be. And I can't get into specific reasons why the shape is this, except that there is this minus sign to show that the pressure is reduced when there is attraction, and that this is n times a square over v square. Why is this? This actually can be worked out. You could have worked it out, and when you are in your studies of statistical mechanics, I don't know how many of you would go to that, you will find ways where this actually can be derived. But this attraction is more like, if you have this. Oh, A is another constant. B is constant and A is constant. Okay? These two are constants. So here we are. A and B are constants, and you see, if you have to look at energy of interaction between particles, which I will actually call potential energy, potential energy, and as a function of distance between particles, then at very close distances there is strong repulsion, this wall-like repulsion. You can't get any closer than this, positive potential energy. And at very large distances, this is of course zero potential energy. But as they come closer, it will become attractive, negative potential energy. And then, of course, somewhere in the middle, it will have a shape of this kind. This is actually the shape of interaction between particles. And the second term is a result of this negative interaction, and the first one is a result of this repulsive interaction. Okay? And you can make proposals on the shape of potential, but that will come into later. Okay? So we have looked at, we know now what ideal gas is. We know the gas laws, and the gas laws give rise to an equation of state, and this equation of state is for ideal gases, and we also speculate on what the equation of state would be for a non-ideal gas, for a real gas. But this was the point we're trying to say, that the state of the system is given by these thermodynamic variables, and there will have to be some kind of relation between them which describes the state of the system. I will take you a little away from this discussion and will take you into to look at another thing, which is again something that you have done in your earlier studies, but we need to remind ourselves of that, because there are a couple of interesting things in there. Kinetic theory of gases. In the kinetic theory of gases, we try to actually understand the behavior of gases from the point of view of individual particles. This is different from statistical mechanics, where again you try to understand the macroscopic behavior from microscopic considerations. Here you also do the same. You try to understand the macroscopic large-scale behavior from microscopic details of the system, but not quite as much detail as you would in the case of statistical mechanics. Here you would be trying to use some arguments about the kinetic motion of particles and try to deduce some important conclusions from it. And this would be good to go through it. So here the first assumption of the kinetic theory of gases is that all the material that we work with in thermodynamics consists of atoms and molecules. Okay? So when somebody put forward this proposal some 100 years ago, 150 years ago, this was a novel assertion, not an old assertion. That look, the gases that you deal with are actually consist of atoms and molecules, and therefore try to understand the behavior of atoms and molecules, gases from atoms and molecules. And that these atoms and molecules, the second point is that these atoms and molecules are in continuous motion. And from the kinetic energy of these atoms and molecules, you can infer some conclusions which will be valid for thermodynamics. Again, the gas is low density gas, nearly ideal gas, and no interaction between particles, and that only particles collide with each other as well as with the whole, so molecules, atoms and molecules have kinetic energies. And hence the name kinetic theory of gases. And that these give rise, their motion, their kinetic motion gives rise to understanding of the pressure and the equations of the state, and the relations between pressure and volume and other quantities. So you look at a gas in 3 dimensions. You have X here and Y here and Z here, and you actually have a box. You consider a box in here. This box has a side L, cubical box, side L. All sides are equal and contains gas. If you want to find out pressure from these considerations, pressure is defined as force per unit area. Force, according to Mr. Newton, is change in momentum with respect to time. Okay, I put this small half arrow on top to be precise by saying this is a vector quantity. So this P, small p that I have written, lowercase p stands for momentum, linear momentum. Force is this. Therefore, pressure ought to be delta P divided by delta T, and per unit area divided by area. So on a given area, if we find out the rate of change of linear momentum, then pressure can be calculated. Change of linear momentum of what? You're saying particles are in continuous motion, and this continuous motion in all possible directions. The particles will go and strike the surfaces of this box. So they will come and they will strike the surface, will go back, will go in another direction and continuously strike the surfaces. Because they strike the surface, they will pass on some of their linear momentum to the wall, or actually they will change their own linear momentum, from which we can see how much of linear momentum has changed with time, and that change of linear momentum with time divided by the area of a wall will give us the pressure, value of the pressure. Okay, this is the whole scheme. So we focus on particle of mass m velocity v and in a random direction. So velocity has components along x and along y and along z directions. Let us look at only one side. Let us say this is the side that we want to look at. We look at this side, we call it face x, which means the face which is perpendicular to x. The face which is perpendicular to x. So this is what we call face x. This is perpendicular to x. Okay. We look at that face x, which is what I have drawn over here, and particles will actually, any particle will come this way and strike this surface somewhere and will go back. We look at only those collisions in which particle comes in vertically, impinges on this and then goes back. This is a very poor simplification, because particles certainly will not always impinge the surface perpendicularly. But then, on the average, the things that we finally average out, it will come out to be decent way of looking at things. So the particle comes in with a linear momentum which is equal to m times vx. Okay? It comes in with a linear momentum m times vx and then goes back after an elastic collision with the wall, goes back with a momentum minus m times vx. Okay? It comes in with a momentum m times vx, goes back with the momentum minus m times vx. So change of momentum is of the particle is equal to minus twice m times vx. This is the change in the momentum of the particle. And now we invoke Mr. Newton's third law. We say there is an equal and opposite amount of reaction. As a reaction, the wall actually experiences a change of momentum phase x. We said phase x? Yes. Phase x experiences a momentum change of delta p of plus 2 m times vx. Okay? So now I will start using the exercise. So the change of momentum that phase x experiences is plus 2 times mvx, and therefore, and also, if a particle wants to come again and hit it, the time it takes for the particle to come and hit is to hit again. Is total distance it travels divided by the velocity, the speed. The total distance it travels is about L in this direction and L in this direction. So it is twice L over Vx. Dimensionally this should be correct because V has dimension of length over time and this is dimension of S, so time will come up and dimensionally correct. So time taken by a particle to hit phase again is this. So from that one can actually say that so now we know this is what we wanted to write as delta t, and this is what we wrote as delta p, and therefore force F is twice mvx divided by twice L over px, and pressure therefore is equal to the same quantity. This quantity is equal to twice m over L times Vx squared. So pressure कोई प्रॉब्लम हो गई समझने में, तो बहुत देर चला गया है क्या हुआ? 2 tenses with 2, yes, I'll go to that, yeah. उसके अलावा भी कोई और सवाल कुछ प्रॉब्लम है नहीं? Okay. No, that is instantaneous. Collision is instantaneous. So the question that he asked is that the time delta t that I took between two successive collisions. And he said that shouldn't that time be actually the time of impinging on the wall? Because that would be the pressure. See what this was your question, right? And the answer to that question is that no, the time, the collision of the particle with the wall is supposed to be instantaneous. That delta t is 0. Okay? The point is that pressure is viewed in this whole picture as particles coming in and one after the other in all sorts of directions, coming in and impinging their linear momentum, giving their linear momentum to the wall. Okay? Wall is rigid, can't go anywhere, it is standing over there. But because they are coming in and continuously impinging and giving their linear momentum to the wall therefore feels this change of momentum with time. Okay? That is why we have to take this. Now, and therefore it will be basically impinging and this giving away of momentum by every part of the gas. Now, what we are considering over here is that there is a particle that goes in and gives this momentum, comes back and does the same again, and then goes back and then does the same again. And how much time does it take, and what is the rate of change of this? And then we will sum over all particles. Okay? In this very simplified picture. So the picture is that the time is that of how many collisions you make, how many times you go and hit the walls. Okay. This was a technical discussion. Conclusion is I should not sit on this table. Not within my back pocket. Good. Okay. So here we are. I think this statement was correct that I should cross out U and not write 2 over here. And therefore pressure is equal to M1 over A, the area that we said over there, over L times Vx squared, which is area times length is volume. So M over volume times Vx squared. Okay? I will actually keep it L cubed because area is L squared. So volume, I'll introduce volume later. I will say this as M over L cubed times Vx squared. So all the particles come and strike that. All the particles come and strike that wall and give away some of its momentum to the wall, linear momentum. So pressure on that particular wall, P, is equal to M over L cubed times. Particle 1 comes in and gives this velocity squared, particle 2 comes in and gives this much, and so on. And there are n particles come in and give this much of momentum to the wall. And since we can put this in a slightly better form, we know that rho mass density is mass divided by volume. Volume is L cubed, and mass can be, I am writing this as mass of a particle times number of particles divided by L cubed. And therefore M over L cubed I can write as rho over n. So this is actually, permit me, change this over here, rho over n. And when you sum a few quantities, n number of quantities, and divide by that n, number n, what you actually are doing is taking an average. So rho is V x squared average. Correct? Because sum over n quantities divided by n is the average, and that average, the sign of the average is this bar. And now we also say that this is Vx squared. Now Vx is the same as Vy is the same as Vz, and we will say that these are all the same quantities. In fact, I shouldn't say this. Vx squared average is the same as Vy squared average is the same as Vz squared average is the same as V squared. So now V is the total velocity. This is the velocity. This is not a speed along x direction. This is wherever it is, average speed. And therefore pressure, and therefore Vx square average happens to be 1/3 of the average speed, T squared. Which means that the pressure we calculated over here is 1/3 of rho mass density times V squared average. Okay. I am not clear somewhere. People are expressing this.
Should we multiply by rho V?
Say it again.
Shouldn't it be 3 multiplied by density into V squared?
No. No. We are replacing. Okay. The question that he asked is, shouldn't this be not dividing by 3 but multiplying by 3? This was the question, right? Okay. And the point is that we are replacing Vx squared. Vx squared, V squared average is, okay, V squared is Vx squared plus Vy squared plus Vz squared. Okay? And these are all equal. So the 3 times Vx squared is equal to V squared. So this will also apply to averages. And therefore this will be 1. That answers the question, right? And then from this actually one can 1 over 3 times rho times V squared. This is a good result because it relates a macroscopic quantity, which is pressure, with a microscopic quantity. Although it is not microscopic anymore because average has already been taken out. So average quantity is supposed to be not quite microscopic, but velocity of particles is a microscopic quantity. I can't lift this board up, so my writing will not be. Right. Yeah. Sorry. Thank you very much. Thank you. I should have said is equal to 1/3 of V square average. Thank you. Thank you for pointing out. Sorry about that mistake. Okay. Now, now pressure on wall X is the same as pressure on wall Y is the same as pressure on wall Z. Is actually the same as pressure in the gas of the gas, wherever it is. Pressure is not something which you can say that that on the wall X should be added to that on the wall Y should be added to that on the wall Z. No. Pressure would be a quantity that is not an extensive variable. I have not defined extensive variables yet, but because it is not an extensive variable, it is whatever the same kind of pressure. A vessel experiences the same kind of pressure everywhere inside the system. So if you have a system, I am just drawing a system, hypothetical system, and you say it is at pressure P, then every part of the system is exactly at the same pressure. If suppose one part of the system is at a different pressure than another system, so it is P1 over here and P2 over there. If this pressure last statement, okay? I know time is up. If P1 is not equal to P2, then the system is internally not in a state of equilibrium. And there will be forces generated within the system so if no, this is not. So if P1 is not equal to P2, there will be forces generated within the system to create that equilibrium between them. Pressure will have to be equal. And because of this, if a system is in a state of equilibrium, pressure at each and every point within the system has to be the same. Okay? Now, which actually brings me back to saying that although we calculated pressure only on wall X of the system, but that defines the pressure of the gas everywhere. That is what the pressure is everywhere. I will take it up from here onwards in the next lecture. Thank you very much. Any questions?